It's time for another amazing chemistry video with Mr. Stapleton, proudly sponsored by Farmers Union Nice Coffee.
Hi guys, welcome to the third video and the first part of the final topic. If that makes sense, hopefully it does. This first topic, 4.1, is all about energy. So far we've been through and looked at fuels, fossil fuels as energy, alternative sources of energy. In the last video we went through and we had a look at calculating energy changes using from the burning of fossil fuels. And for this last one we're going to be looking at the use of galvanic cells as an alternative way to produce energy to burning fossil fuels. So a galvanic cell is known by a few names. It's also known as an electrochemical cell or a voltaic cell. Discoverer of this cell was Alessandro Volta, an Italian chemist, and he discovered that when you have two different metals and a solution that conducts electricity between them, you actually can produce an electrical current through a spontaneous chemical reaction. Okay, so this is going to be all about redox reactions in here as well. So the transfer of electrons through reduction and oxidation. So there will be there's a link later on to a YouTube video around refreshing yourself on half equations. I suggest you do that. So some of the things you need to know around electrochemical cells, I'm going to actually go through what's here using the next slide. So this is an example of a galvanic cell. Okay, what we have is two half cells. So this is half of the cell, this is half of the cell as well. Together, these are what produce the electrical energy via spontaneous chemical reactions. So here we have one half cell. I'm going to start on this side, which is called the anode. Okay, in this case, the anode is negative. Okay, and I'll get through how you remember all this in a minute. And at the anode we have oxidation occurring. Now oxidation is what we call a loss of electrons. So we have two metals, zinc and we have copper. Zinc is the far more reactive metal, okay, and so reactive metals very much want to lose electrons. So you can see the zinc here is losing electrons to form zinc ions. So what's happening is that this zinc electrode, now an electrode is just a material that conducts electricity. This electrode here is sitting inside a electrolyte. Now, an electrolyte is something that conducts electricity. Okay, in this case, we're using zinc sulfate. Now, the sulfate one, you'll notice we're using the sulfate for both. Sulfate is really good as the anion in an electrochemical or an electrolytic cell because the sulfate generally doesn't take part in oxidation or reduction. So it's inert, and that means we can have the electrodes being the things that we have the reactions involving. So this zinc electrode here is going to be giving up electrons, so it's going to be producing Zn2+ into solution, and it's going to be producing electrons which are going to come out through this external wire. So eventually this electrode will be eaten up, okay, as it's converted into zinc ions. Now I'm actually just going to use my little drawing tool in here as well. Okay, so we're getting zinc ions being built up here in solution. Okay, over here on this side, what's happening is that we have copper, and because copper is less reactive, what it's going to be doing is picking up the electrons, so that's a reduction. Okay, and this is the positive electrode over on this side. Okay, so what's happening is that we have copper ions in solution here. These copper ions in solution are going to be picking up electrodes, and we're going to be depositing solid copper onto this electrode. So what that means is that this electrode is going to start to grow in size as we get pure copper deposited on it. Now, the electrons flow through the external wire here, and if we connect a load to this, here we've got an ammeter so we can measure it, but if we connect a load, we can actually use those electrons as a power supply. Okay. Now, the unique thing that we need in an electrochemical cell is what's called a salt bridge. Now, a bridge is obviously something that connects two different things. Okay. We use a salt bridge here, and we've got ammonium ions, and that's actually NH4+. And that's Cl-. So I'm just going to change my pen color here. So that's NH4+. I'll just make that quite clear. That's ammonium ions, and we've got chlorine ions here. Now over here on this side, what you've got to remember is that we're getting a build-up of zinc ions in here. So initially the zinc sulfate here had no charge, okay, because we had zinc ions and sulfate ions. But we're building up the zinc ions here, so we're increasing the positive charge. So we're increasing the positive charge over here. Over this side, we initially here had copper ions and sulfate ions, so that was no charge, but the copper ions are being picking up electrons to form solid copper. So over here we're actually increasing our negative charge. Now what happens is initially we had two neutral species, alright, but now we're getting a difference in charge between the two of them, and we're going to be trying to push electrons over here to a negative solution. Now what we've done is what we call lost the potential difference between the cells. So what we want to try and do is keep these cells neutral. So what we do is we have our ammonium ions, NH4+, they come down and will offset the loss of the copper ions, and they will balance out the negative sulfate ions that we've got in there. What's going to happen is our chlorine ions here are going to come down into solution, and they're going to offset this build-up of positive zinc ions that we've got, so we can keep our electrolytes neutral and we can keep our electrons flowing through the wire. Without your salt bridge, no electrons flowing, no electricity produced. Okay, so that's a electrochemical or a galvanic cell very quickly. I suggest if you need to that you look at the video here, okay, which just goes into a bit more depth and shows some of the different galvanic cells and how we produce electricity from them. Okay. Now, what you need to know is how to work out which metal is the most reactive. Okay, and you use that by using what's called a metal reactivity table. Basically, if you remember your trends in the periodic table, metal reactivity increases down a group and decreases across a period. So what that means is the most reactive metal you'll go to is francium. So if you kind of work from francium in that bottom left-hand corner of the periodic table as you're looking at it, and then work out from there which one's closer to francium, that's a good way of indicating which one's most reactive. The most reactive one will be the anode and will undergo oxidation or loss of electrons always. Alright, and electrons will flow from the anode, where oxidation is, to the cathode. Okay. There are three types of galvanic cells. What we are used to is things like batteries. They're primary cells. They're ones that cannot be recharged. So you connect your battery, electrons flow between the anode and the cathode. Okay, once you've used up all the chemicals within your electrolyte, the battery goes dead and you have to throw it out and use a new one. Secondary cells, you can have what we call batteries similar to that as well, but they're rechargeable, so that's the main difference. So they produce electricity via spontaneous chemical reactions, but you can then put electricity into them to regenerate the chemicals, and a car battery is a really good example of that. Okay, and a fuel cell is something that has a continuous supply of reactants, so I'm going to cover those a little bit in a minute as well. So couple of rules to remember. These are the ways that I teach my students how to remember and identify what's happening at each of the half cells. So the first thing to remember is oil rig. So oxidation is a loss of electrons, reduction is a gain of electrons. So if you remember which metal is the most reactive metal, that's going to be the anode, alright? And you use the next thing, vowels. OA, oxidation occurs at the anode. Alright, so if you remember that, obviously then reduction occurs at the cathode. Then in the final thing, if you need to work out the charge of the electrode, if it's positive or negative, I teach my students to use the word GANI. Alright, so it's a bit funny. But in a galvanic cell, the anode is negative. In an electrolytic cell, the anode is positive. So if you use these three little tips or tricks, that will help you to be able to pretty much identify, given the information, an entire electrochemical cell. The first step is always, though, identifying which is the most reactive metal. It's the one that's closest to francium. The most reactive metal will be where oxidation occurs. That will be the anode, and you can go through and work out the rest from there. So I did talk about fuel cells. So a fuel cell is a galvanic cell. All right, they are unique in that they have a continuous supply of electrode reactants. So unlike a conventional battery where you use up all the reactants and you have to throw them away, you are continuously putting reactants in to be able to have a continuous supply of electrical energy. Okay, they have a cathode and an anode exactly as a battery did. So this is an example of a fuel cell. This is a hydrogen fuel cell. I'm going to go through that because it's on the next page as well. So the cathode is still where reduction occurs. So you get hydrogen gas coming in. What happens is that the hydrogen gas, H2, loses electrons to form H+. Okay, so I'm going to write out that half equation here. So H2, okay, forms two lots of H+, and two lots of electrons. So you can see the electrons here which are now flowing from the anode to the cathode, just as they would in a normal electrochemical cell. Okay, what happens over here at the cathode is we get oxygen coming in. Alright, so I'm going to change my pen colour to match sort of what they've got. So I've got green. So we've got oxygen coming in. Okay, the oxygen picks up some electrons. So in this case, it's going to pick up 4 electrons, and you'll see why in a minute. Because what we're forming is oxygen ions, O2 minus. Alright, we need 2 of them. Okay, and what happens at this is that these oxygen ions and the hydrogen ions here, so the oxygen ions travel through the electrolyte to the anode. Alright, they link up with the hydrogen atoms and they form water here. So the real benefit of a fuel cell like this is that we produce water as a product. Okay, which is really, really useful. Okay. This is a slightly different version, alright, which is an alkaline hydrogen fuel cell. So in this case, instead of having H plus being formed, what we're doing is using an aqueous alkaline solution. So here in the middle, we've got potassium hydroxide, which is a base. Okay, and you notice the anode reaction is slightly different. Instead of H2 forming 2H plus and 2E minus, it now picks up hydroxide ions and forms water with electrons. Those electrons travel through the wire to the cathode, where the oxygen picks it up to form more hydroxide ions. Okay, so those hydroxide ions replenish the ones that the hydrogen is using. Okay, and so this reaction continues as you continue to put hydrogen in. Okay, you get water out as your product again. So you can do it under acidic or basic conditions. Okay, what I have got here, this is the YouTube link which goes through half equations, which you might want to revisit if you need a little bit of practice. I do right at the end of that go through a half equation under alkaline conditions, so that might be beneficial for you as well. So if we're looking at the main advantages of fuel cells, okay, and solar panels, and they're probably the real main ones in particular, is that they actually generate electricity directly. So you connect up your anode and your cathode in your fuel cell, and straight away you're getting electrons produced which you can use to power things. Same thing with a solar panel, that's directly generating electrons which you can use to power things. Traditional burning of fossil fuels, and I've shown it here in the diagram, is that you burn the fuel, you heat up water, that water turns into steam, that steam goes past a turbine and causes this to spin. Alright, so now we're getting to the bit where like wind energy was the same. Okay, that turning turbine, alright, uses electromagnets to create an electric current. The problem is you've got a lot of heat that's lost, okay, so they're inefficient. Alright, you're burning the fuel here and you're losing heat, which could be used to obviously heat more water, hopefully, but it's a bit inefficient. Whereas in a fuel cell or a photovoltaic cell, you're actually generating the electricity straight away, which is quite beneficial. Some other advantages, they're more efficient, which is what we've just said. They're environmentally friendly, no harmful waste products. We're producing water as a product, which isn't harmful. They're quieter, they have no moving parts like a combustion engine. They're more reliable because you don't have those working parts that can break down. Okay, they use readily available fuels and oxidants. It's quite easy to get hydrogen and oxygen gas. Oxygen is obviously present in the air. Hydrogen you can get from electrolysis of water, and the electrodes are not used up as they can be in some of those other electrochemical cells we looked at, so they tend to last longer. Disadvantages of fuel cells, okay, is that they're much more expensive currently. The technology isn't that great. Some of the electrolytes are quite corrosive, so if you're using that potassium hydroxide one, for example, that's very similar to oven cleaner, so that can turn your skin into soap and it can cause burns. It's commonly called things like caustic soda. You use medium to high temperatures, which is expensive, can be a little bit dangerous, okay, and any impurities, if you get impurities within the fuel, so the hydrogen or the oxygen that's coming in, that can ruin the electrodes, and you have to replace the whole cell, which can be quite bad. One of the new advances in fuel cells is actually something called flow cells. Now, flow cells are fuel cells that are rechargeable. Okay, so we have two chemicals here, so we've got a continuous supply of reactants like we did for a fuel cell, but the difference is that this time we can then recharge this, okay, like we can a secondary cell. So it's kind of the next step where we've got a continuous supply of reactants which can produce electricity, okay, and then we can store that electricity and then regenerate that electricity in a flow cell. So they're an excellent choice for large-scale energy storage. This is probably one of the ways that's really going to be going ahead in the future. Alright, so main thing you need to know for the moment about flow cells is that they are basically fuel cells, so they have a continuous supply of reactants, but they are also rechargeable, which is quite beneficial. Alright, 3 videos in, that's only the end of the first part of this topic, which is 4.1 on energy. So I suggest you have a look at these, make sure you've got a good understanding of them. As always, check out those other YouTube videos if you need more help. And if you've got any questions or you want access to this PowerPoint, leave a comment in the section below and I'll get back to you and let you know how you can get hold of it. Alright, good luck guys, and thanks for watching.